Well, I hope to share with you what I find exciting about adaptive optics, which makes clearer images, and some of the things that we're learning from it. And I'm interested in galaxies that collide with each other. And we asked the question, what happens when two galaxies collide if each one of them is carrying its own giant black hole, and will the black holes eventually merge? So that's sort of the quick summary. So I'll talk about turbulence in the Earth's atmosphere, because that's why we need adaptive optics. And then using this technology to study merging galaxies. We'll speculate on which of the black holes in these galaxies will eventually merge and make a burst of what's called gravitational radiation. Who's heard of gravitational radiation? Okay, so we'll talk a little bit about that. And then if there's time at the very end, I threw in some secret extra slides for you. So first, why do we need adaptive optics in astronomy? It's turbulence in the Earth's atmosphere that limits the spatial resolution, how clearly a telescope can see. Turbulence, you know, is why stars twinkle. Sometimes my husband accuses me of untwinkling the stars. But more important for astronomy, it spreads out the light. For example, if you look at a star with a big telescope, it ought to look like a point, and instead it looks like a fuzzy blob. That's a technical term, fuzzy blob. And we're trying to fix that. So even from ground-based 8 to 10 meter telescopes where the mirror is as big as this stage, because of this turbulence, we have no better spatial resolution than a little 8 or 10 inch telescope that you might have in your backyard, or that your uncle may have shown you in some star party. And that's pretty pathetic, right? I mean, why are we spending all this money? Well, of course, we're spending the money because a telescope this big can collect a lot more light than a telescope that big, but we want to also see more clearly. So you can see if turbulence affects, let's see if I can make this work. Even with a small telescope, this is a crater on the moon. And you can see the effects of turbulence both by image motion and by blur. We'll come back to both of those things. So here's the impact of that a little bit more quantitatively. These are 3 images of a bright star, a star called Arcturus, which some of you may have seen every once in a while. If you take a long exposure image of a star through all the turbulence, here's the fuzzy blob. It's about 1 second of arc across if you're lucky. And that fuzzy blob, if you take a bunch of snapshots, doesn't look at all like a round thing. It looks like a bunch of these little speckles, spots. And each one of those spots is made by some aspect of the turbulence in the atmosphere. And of course, the next millisecond, it's always changing. So the next millisecond, you'll have a different bunch of these speckles. And if you integrate for a minute in a time exposure, sure enough, they sort of average out to this great big thing. But what we're trying to do with adaptive optics is take these little speckles and pile them on top of each other. Quite literally, it's all done with mirrors. And then you get a much smaller spot. In principle, you learn in physics class, even in high school physics class, that the smallest angle that a telescope can resolve is given by the wavelength of the light divided by the telescope diameter. So we ought to be able to see smaller and smaller things, more and more detail, the bigger the telescope. And what I was whining about in the last slide was that's not at all what happens, and now we can make that happen. Okay. So this is a short exposure image of a bright star. You'll see it's very much spread out. Of course, this is very magnified and very slowed down. These changes are happening on millisecond timescales and over tiny little regions. But the image is not only blurred, the centroid of the image is moving around, right? It's here, now it's there, sort of hopping around. And we want to fix both of those things. So this is what I call the cartoon approximation to how adaptive optics system works. So here's your favorite galaxy that you want to study. or at least take a picture of. And you're very lucky you have a bright star that happens to be near your galaxy, and I'll tell you what happens if you don't have a bright star, but for now, you have a bright star. And these are close enough that the light from the star and the galaxy go through the same turbulence. So you can use the light from a star and analyze it with a very fast detector and figure out what shape that you should put on a special deformable mirror. Picture a mirror that's this big on a telescope that's this big. This mirror is behind the main mirror of the telescope, and the trick is it changes its shape 1,000 times a second. So this computer uses the information from the turbulence and tells the deformable mirror a shape that it should take that'll cancel out the blurring of the turbulence. In optics terms, it cancels the aberrations from the turbulence. So and I have to point out, my son tells me, Mom, this computer is hopelessly out of date. You should use a modern one. So I'm tempted to put an iPhone up there or something. But OK, so this is a little more technical. Here's what an adaptive optics system is. In an optical diagram, the telescope is way up here. The light comes off the main mirror of the telescope and goes into your adaptive optics system. It's distorted. And one of the first things it sees is this mirror, which is changing its shape constantly. After the light bounces off the mirror, it's mostly cleaned up. The wavefronts are flat or planar. I'll tell you in a minute what that means. You steal a little bit of the light from the high-resolution camera or spectrograph or whatever your main instrument is that you want to use to study your galaxy, and you send it into something called a Wavefront Sensor. And what that does is it measures the slight imperfections on the light that's still left after it bounces off the deformable mirror. Why would it still be left? Well, you might not have measured the turbulence all that precisely. The mirror might not have gone to the position that it told you to. And time is passing, and the turbulence is always changing. So maybe you're lagging a little bit behind, and you can't catch up. So you're always measuring the lack of perfection of the corrected wavefront, and you send that information into a control system, which for those of you who think about these things is a closed-loop feedback control system. What does that mean? It means that the mirror is always almost perfectly corrected the beam, but not completely, and you're always just tweaking it around that almost perfect beam. So, and one thing to remember is the adaptive optics system, AO system, fixes the image after it's come off the telescope. When people first hear about this, they think, OK, we've got this 8-mirror mirror. We're going to wiggle the mirror to do this work. And guess what? The mirror weighs tons. It's thick. You can't wiggle it fast enough. You can't push on it hard enough. It's better to do it with a smaller mirror. And I'll show you what these mirrors look like. So after you've done this, here's the same image of a star as before. Here it is with adaptive optics. So it's much smaller. It's not perfect. It's still got a little bit of a halo of light around it, but it's a lot better than it started. And I want to point out, let's go back and point out again, that these two images are a little bit of a cheat, because on each one, I made the brightest pixel in the image white. And that indicates the highest intensity. But I did it separately. So the brightest pixel in this image is white, and the brightest pixel in this image is white. But that's a fake, because what you've done is you've gathered all this light from this huge real estate on the detector and piled it into just 1, 2, 3, 4 pixels. So this intensity in reality is much brighter than that one, and I'll show it to you in a minute. So this is what it actually looks like. This is the image without adaptive optics that we saw before. This is with adaptive optics. And now on a scale where intensity is the vertical axis and the position on the sky is shown in X and Y, this is the speckled image that isn't adaptively corrected. And you collect all these photons and put them in just 2 or 3 or 4 pixels, and the intensity of the light in that very small region goes way up. So you got better contrast in addition to better resolution, sharper images. Why does contrast matter? You've heard, I hear, that there are now more than 4,000 planets that have been discovered around nearby stars. They're called extrasolar planets. And if you want to image one, you got a little problem. The planet is typically 1 million to 1 billion times fainter than the parent star. So if you don't have adaptive optics, is this the planet? Is that the planet? Is that the planet? Are they all speckles from the turbulence in the atmosphere? There's no way to tell. If you correct the light and you do it really, really well, you can see a little planet down here because you've put all the light from the star in a small number of pixels. So that's why it's a good thing to do for planet detection. So when we first started out doing this at the Keck telescope, we were looking at Neptune, which is about 2 seconds of arc across. It's an infrared light, and what you see as these bright bands are high-altitude clouds. And they're zooming around, carried around Neptune by its winds, which are very, very fast. And so that's why they get dragged out. If you start out with one cloud here, a few hours later it'll be dragged out into one of these bands. So this is what the Keck telescope would do, or did, on Neptune without any adaptive optics at all. Here's Hubble in the infrared, 1.6 micron wavelength, infrared light. It's a relatively small telescope, 2.4 meters. It doesn't have any turbulence in the atmosphere. It does a much clearer job. It looks a lot better than that. But remember I said that the resolution of a telescope, ideally, I think I have this here. Ideally, you can do more and more clearer imaging with a larger and larger telescope. The resolution goes like wavelengths divided by telescope diameter. So here we are, we've got a 10-meter telescope. It's 4 times bigger than Hubble. It's been all corrected, and it does, sure enough, quite a bit better in terms of seeing the detail. In fact, we've made maps of not only the clouds, but all the velocities in the upper atmosphere, just watching Neptune rotate in front of us. Hubble still has advantages over adaptive optics. The field of view of Hubble is much bigger than what you can correct with adaptive optics, because with adaptive optics, if you correct the turbulence in this direction, it's going to be a little different in that direction. So after you get far enough away from the center of the field, you start getting fuzzier and fuzzier. And also, adaptive optics, at least now, is hard to do in optical light. Green, we can do it in red light, but we can't do so well in green light. Blue light is very hard. Ultraviolet light is impossible. And it's not, in principle, impossible, but we can't do that yet. And so Hubble is the way to go if you need clear imaging in green or blue or even ultraviolet light. I think under the right circumstances, adaptive optics on big telescopes can be a lot superior to Hubble if you're looking in the infrared wavelengths. So I was pretty glib. I said, oh, this deformable mirror adapts to the turbulence and it fixes it. Well, how does it fix it, right? So this is, again, a cartoon approximation. And I want to say what these diagrams mean. This is called a wavefront. A wavefront is a surface of constant phase as a wave travels through space. If you move from side to side along the plane of a wavefront, the field will always have the same phase. So now I've depicted a plane wave by just a line on the screen, and you should imagine that line comes out of the board as a plane, so it's representing the plane. So now let's see, I have an idealized aberration. It has a notch in it, and this part of the wavefront is lagging behind that part. If I make a notch here on the deformable mirror that's half as deep, then by the time the light's gone in and out, the back had time to catch up with the front because the front had to travel farther. So I've made it into a plane wave. Now this is just a flat plane coming out of the board. So of course we don't have notches, right? We don't have nice square things, but here's a sort of a depiction of what an actual deformable mirror looks like. Picture a thin sheet of glass, and you've attached to the back of it with glue. You should worry. You've attached to the back of it glue that are actuators that get longer and shorter when you send a different voltage to them. So each of these actuators has a wire coming out. It's changing the voltage, and they change their height in response. And they just push and pull on that thin piece of glass, which can change its shape. So it's the same kind of thing. This part of the wavefront is in front of that one. You make it travel farther, and when it comes out, it's a flat wavefront, more or less. Here's what one of these things looks like. This is at Mount Palomar. So here's the deformable mirror, the face of the deformable mirror. One of the biggest disillusioning events in my escapades with this technology is the first time we turned on our adaptive optics system at Lick Observatory, I wanted to climb up and look at the mirror. I was sure that I would see it going like that. These changes that it makes in its shape are so small that we can't see it. They're 35 to 100 or 150 nanometers. Very, very tiny. You can hear it whirring, but you can't see it. That's not fair, but anyway. Okay, so on the back, each of the actuators has a wire coming from it. This is 4,356 actuators, lots and lots of wires. I joke that if somebody's giving you a tour of their I/O system in the lab and you don't really know what you're looking at, there's too many mirrors, there's too many things happening, cameras, all sorts of stuff. You can make yourself seem very smart by finding the object on the optical bench that has all these cables coming out the back. And that's the deformable mirror. Each cable is, is needed in order to send a signal to the mirror about what shape it should have. So this is one kind of mirror. This is a few inches across. There are many other kinds. So this is the same kind of mirror we were talking about before. This is the biggest one that has been made so far, I think, of 1,000 actuators before the one that I just showed you. And this is the face of it. It doesn't look reflective because you haven't put the little coating on it that makes it shine light back. So you can actually see the actuators if you stare at it hard. You can also make a mirror with 1,000 actuators using the techniques of Silicon Valley, of photolithography. So these are microelectromechanical systems, and each of the 1,000 degrees of freedom is a little capacitor that pulls down on a membrane and changes the shape of the membrane. Same exact principle. This is a little reminder of how most current telescopes work. The light comes in from the sky, it bounces off the primary mirror, it bounces back to a secondary mirror, and then usually either down through a hole in the primary mirror or perhaps to the side where you have other instruments. So back down here and over here, you have the instruments that measure the light. They can either make an image or take a spectrum or measure polarization. And what people have done in Italy at Arcetri and the University of Arizona is you take out the mirror that came with the telescope from the store and you replace it with an adaptive secondary. So this is upside down, but this is the surface that will ordinarily face downward. And again, there's the wire, so you know that's going to be changing its shape. Each one of these things is a little electromagnetic actuator that gets longer and shorter. They're sort of that big. And again, they haven't put the reflective surface on it, so you can actually see what's going on. So I'm going to transition to things we've done with these technologies at the Keck Observatory in Hawaii. That just happens to be a UC telescope. There are many other observatories in the world that do this. So the Keck telescope is a little unusual. Instead of having one round, thick piece of glass, it has 36 hexagonal segments. Each one of them is about 1.8 meters. They're controlled by edge sensors that keep them in a perfect, smooth configuration, and it works really well. So again, the light comes down from the sky, bounces off the primary up to a secondary, and in this case, it goes to a little tertiary mirror, a flat mirror that can send the light sideways to these platforms that are called Naismith platforms. They're about as big as this stage, maybe a little more. They're like your living room practically. And so you can fit a lot of big old equipment on them. For those of you who haven't seen pictures of the Keck telescope yet, This is what the primary mirror looked like before they put on the last ring of segments, just so you can see the hexagons here. And that's the Naismith platform that I was talking about, where the adaptive optics is. And this is a person. So he's sitting in the cage that holds the tertiary mirror. So this is really big. I thought I'd tell you a little bit about the history of adaptive optics in general, because it's a very nice story of the interplay between work that was done for the Department of Defense and work that was done for the astronomy community. And initially, those were completely separate, and now they've sort of converged in a nice way. So the history interleaves advances in the military and in the astronomy community. First, suggested by Horace Babcock, an astronomer in Pasadena in 1953. He had all the right ideas. He published 2 papers on it. The technology was absolutely not there. He had no idea how this was going to actually be implemented, but he had all the right considerations, and he's sort of, I guess, the father of this. In the 70s, there was a lot of theoretical work done by people like Freeman Dyson, whom you may have heard of, Francois Rodier in France, David Friedman nearby in Monterey, and so forth. In 1977, up at Lawrence Berkeley Lab, Louis Alvarez's research group did what I think may be the first experiments using an adaptive mirror. They didn't quite have the technology to make a whole mirror, so they just did a vertical strip of mirror. So it's like a long, skinny rectangle with actuators glued to the back. And they showed that you could sharpen an image somewhat. Things really took off in the early 80s. Some of you may remember Star Wars back under President Reagan. And part of Star Wars was he wanted to use a laser shot up from the ground to shoot down missiles or satellites or something. And if you're going to shine a laser up through the turbulence, you'd better correct it with adaptive optics, or by the time it gets up to 400 kilometers, it'll be practically a kilometer across. It's not going to do anything to anybody. So the military, and particularly the Air Force, was interested in this. DARPA was funding some of it, and there was work done at Lincoln Labs. It was largely secret, although I did get to see one of the very early, completely analog adaptive optics systems, all done with RLC circuits and lots of wires crossing all over the place. And it kind of worked. It did okay. It was on Maui. In the early 1980s, there's a group of people called the Jasons, which get together every summer to try and address problems for the government, usually federal agencies of various kinds. And for the Department of Defense, they were asked to look at this issue of how do you correct these Star Wars laser beams going up. And also, they were interested in imaging. At that period of time, the Soviet Union was launching a satellite per day. And frankly, we didn't know what most of them were. You know, oh, there goes another satellite. I wonder what that one is. So they wanted to take images of these satellites. And again, in order to do that, it's very like imaging a galaxy. You have to correct for the turbulence at the bottom of the atmosphere. So in Jason, we took an idea that had originally been suggested in a completely different form by the military, and we came up with this idea of what's called sodium laser guide stars. Do you remember those ugly, dark yellow sodium street lights that used to be all around San Jose? There still are in some places. So they are glowing in the transition of sodium atoms. It's a ground state transition. And they make this yellow light. And guess what? That's the color of our laser light. And I'll tell you a little bit more about why that is. So today, there are active adaptive optics programs in the military and in astronomy, and things aren't secret anymore. There's a lot of interesting give and take between the two groups. And just as we were hoping, just about every 8 to 10 meter astronomy telescope on the ground that does imaging at all has an adaptive optics system. So what about this laser that I talked about? Why do we need that? So I said before in this cartoon that you can look at your favorite galaxy and correct it with adaptive optics if you have a way to measure the turbulence. And the light from your star has to go through the same turbulence as the light from your galaxy, or else you'll be correcting the wrong thing. They'll just still be blurry. So if they're too far apart, the light from the guide star is going through different turbulence, and it's not going to help you at all to measure it. So what we do is we make our own star using a laser. The concept is simple. The execution is not. So you have a laser, typically 10 watts maybe, continuous wave, so average power. It's yellow. You shine it up to a height of about 100 kilometers. I'll tell you why. And you can shine it right at your distant galaxy. And you're guaranteed that the light from the laser will go through the same turbulence. And you use this artificial star up here. It's about this big at a height of 100 kilometers. It's basically a star seen from below to measure the turbulence. And then you can point anywhere. So this is what we did at Lick Observatory initially, and then at Keck. And I have to point out that there really aren't very many bright stars in the sky, right? I mean, if you get out of San Jose so you can see the stars at all, you look up and it's mostly black. Not very many bright stars. And that's true even if you have a telescope and you're looking at fainter stars. If you want to look at a random place in the sky, because that's where your favorite galaxy is, the chances are it's not going to have a bright enough star to do this trick. And so that's why doing it with a laser is so important. So why is it this funny yellow color? It turns out that at a height of about 100 kilometers up in the atmosphere, that's where little meteorites, the size of dust particles, get hot enough as they come down into the atmosphere that they basically burn up and ablate away and leave their atoms behind. So they're moving very fast. They come in typically on a shallow angle. They get hotter and hotter as they have friction with the air. And eventually they just leave their atoms. And the atoms that they leave are iron and calcium and sodium and basically the atoms that are in rocks. It turns out that sodium is the best atomic transition to use. We shine this yellow light, 589 nanometer light, onto the sodium layer, and we excite a spectral line called the sodium D2 line, which is called a resonant transition. It goes from the ground state of the atom up to the first excited state. It's very strong, and we get lots of light back. You could do it with iron or calcium or anything else, but you have to work a lot harder. So all of this, these JSON reports and this work by the Air Force and DARPA was highly classified. And in the early 1990s, a bunch of us, including people in the Air Force and in the JSON group, myself, got involved in saying, look, this shouldn't be classified anymore. The Europeans had independently discovered it. They had published on it. It's pretty obvious what we're doing now. Let's get rid of the classification. And the Air Force ended up agreeing after a while. A society where all was revealed, and the Air Force people stood up and showed their results. And one of my astronomy colleagues from the University of Illinois said, "I've wasted the last 10 years. You did it all already." Which was true. I mean, the classification is not necessarily a good thing in terms of people's time being wasted, because he didn't know about this stuff. But anyway, we wrote this report in the early 80s saying, hey, you may want to use these big lasers to shoot down things up in the sky in Earth orbit, but you can also use them for astronomy. And we actually drew out where you would put the laser and so forth. And so when that was declassified, I was having lunch at Lawrence Livermore in the outside patio of the cafeteria, and I was talking with my colleague, Herb Friedman, and we started talking about this, and we said, darn, you know, people have known about this for a while. The Europeans have been publishing on it for quite a while. Nobody's done it. Nobody's made this big yellow laser. How hard could it be? Little did we know, how hard could it be? So we said, well, look, lasers are good. Livermore knows how to build lasers. Let's see if we can get something started. And so we did. We originally fired the laser from the laboratory site, which is quite interesting. So there's an office building, and there's another office building. They had big lasers that they had built to do what's called isotope separation for civilian nuclear power. You need to enrich uranium in order to run a regular nuclear reactor. And they thought they could do it much more cheaply with using lasers. And they eventually showed you could do it, but all the Russian uranium became available on the open market, and it wasn't economical. So the lasers were over here. There was fortunately an underground pipe which we could send it to, and we just put a mirror at 45 degrees and sent the laser light straight up into the air, and we measured the turbulence. That was the key thing. Is this crazy, or are we going to be able to actually measure the turbulence 500 times a second or 1,000 times a second? And we showed that you could. We also managed to fry many moths. So there was a, this was a kilowatt laser. It was a little crazy. This tube had a piece of glass on top of it, and every morning when we got up after using this at night, we'd scrub off the dead moths. Anyway, so we eventually did it at Lick and Keck Observatory. Keck is in Hawaii, and here's what the original laser looked like, fired off the side of the telescope. Now they're fired off in the middle, which is fine. And again, this was a joint project between a civilian and a quasi-military, or at least classified organization, Livermore and Keck, and it worked out very well. And as I said, today every astronomical telescope has these things on it. This is a movie which probably won't play, especially if I can't find it. Yeah. So this is just the Keck 1 and Keck 2 telescope and the Subaru telescope. And the movie just shows these lasers turning on and off throughout the night. It's a greatly slowed down video so that you see the laser pointed here, and then half an hour later, when somebody's observing something else, the laser moves and points someplace else. So it turns out that lasers really are better than natural stars if the natural star is too far away. So at the center of the Milky Way galaxy, you may know that we have our own little black hole. It's 4 million solar masses, small by cosmic standards. It's right here, in case you want to know. And there are no bright stars around, none. These are all very, very dim. And so Andrea Ghez and her group at UCLA tried valiantly to do imaging of these stars around the black hole. And what her goal was is to follow the orbits of these stars as they go around the black hole, to measure the mass of the black hole, to test Einstein's theory of relativity, and learn about how the centers of galaxies evolve. And so you can see the laser guide star gave much better correction. And lest you worry about these funny shaped stars here, remember that the mirror of the Keck telescope is a hexagon. So if you're doing really, really, really good correction, you should see all these little hexagons. So to somebody like me, it makes my heart go pitter-pat to see all these jillions of little hexagons all around. Okay. So I want to go on to, how am I doing here? Okay. I want to go on to some of the work that I and my students have done on colliding galaxies and what happens to their black holes. And so these are Hubble Space Telescope images of nearby galaxies colliding. It turns out that in the life of an average galaxy, it's collided with another big galaxy a few times, 1, 2, 3 times. And it has a big effect on the evolution of the galaxy. If each merging galaxy brings its own black hole, we now know that most galaxies do have supermassive black holes in their core. And so if they're going to collide, what happens to the black holes when they actually collide and form one galaxy? So we started out by looking at nearby galaxies so we could see a lot of detail, and that had a lot of gas, and we're at the late stages of merging, so they're already within about 1,000 parsecs of each other. So think hundreds of light years away, or maybe thousands of light years away, pretty close by cosmic standards. And they're orbiting each other. And the question is, what happens to them? Are the black holes going to merge? Are they going to keep going in orbit forever? Is one of them going to get kicked out? So fortunately, these galaxies emit very strongly in infrared light, and we can observe infrared light well with adaptive optics. So that's what we did. I hope you can see this. Yes, good. So this is a galaxy called NGC 6240. It has a nucleus. It has these weird tails coming out of it, and I'll show you that that's a result of the merger. It has a bright star nearby, thank goodness. So we use this as the adaptive optics guide star. And it has a double nucleus, and we're going to zoom in on the nucleus. But I wanted to show you first why these tidal tails might exist. So here's a computer simulation of two galaxies colliding, and the tidal gravitational forces of one galaxy on the other pull out these really big tails. And that's how come the galaxy got to look like a train wreck like that. Okay, so we're looking in the infrared at a wavelength of 2.2 microns, and this is what these two galaxy nuclei look like in this tiny little region in the middle with Hubble. So that you can see there are two nuclei. It's not exactly clear where the black holes are, but you can convince yourself that there's something there. This is what it looks like with Keck, 4 times better resolution. You start to see very interesting details, like there are these little star clusters. So these are newborn star clusters that are just 10 or 15 million years old that formed when the gas in each galaxy crashed into the gas in the other galaxy and got compressed and formed stars. Okay. So as I said, we shouldn't be too surprised that the image with a Keck 10-meter telescope with AO is better than Hubble. So, but that begs the question, here's a different way to show that Keck image. If there's supposed to be a black hole in each of these two nucleuses, excuse me, but where is it, right? There's not a sign saying, here I am. Is that the black hole? Is that the black hole? There isn't even a point source in this nucleus. There are several point sources in this nucleus. So we set out to find out where the black holes were, and we did. We located them because they're good emitters of radio radiation. And so there's an array of radio telescopes in England called the Merlin Array. They could measure the position of the radio sources really well, and we were able to precisely overlay those radio positions with that infrared image that we took. And so this one, I could convince myself, like, yeah, that looks like a point source. Maybe that's a black hole. We're not seeing light from the hole itself. We're seeing warm gas that's heated up as it falls into the black hole. It looks like a point. It's not quite clear what's going on here. It's not a point, but what we found when we took an image at a longer wavelength that gets through all the dust that's lying around in this train wreck is the black hole really is right here. So we can actually use a technique called spatially resolved spectroscopy to measure how massive these black holes are. And spoiler alert, there are about 1 billion solar masses, 1,000 times bigger than the one we have. I'm going to skip this equation, but what we're looking at is how fast the gas goes around the black hole. So if you, this is too much to read, but if you we're in our solar system, and you magically, instantly turned the sun into a black hole, all the planets would keep doing what they were doing before, because the gravity is exactly the same. And you could measure the black hole's mass by looking at how far away each galaxy is, how far away each planet is, and how fast it's going around. And that's really what we did. There's a lot of gas lying around in these galaxies, and we just measured its velocity as a function of distance from the position of these black holes, which we now know. How do we do that? Well, there's an imaging spectrometer called OSIRIS at Keck, which takes a full spectrum at every pixel of an image. So this is a cartoon. It's taking a picture of a galaxy, but at each pixel there's an entire spectrum, an entire spread of the light into its different wavelength constituents. And it turns out, there's a law of physics that if you can measure the shift of a spectral line's wavelength or frequency, delta lambda is the shift divided by the original wavelength, you can learn what the velocity is of the thing that's emitting that light. So it's the velocity divided by the speed of light, and you can get a map in velocity space of of the gravity. So this is nothing but Kepler's law. Kepler's law says if you have a point mass here, on this side of the point mass, as you get closer and closer, the velocity gets higher and higher. On the other side, it gets higher and higher, but in the other direction, because you're going around. And so if you smooth out this cusp here, which isn't observable, you get some predicted velocity curves that look like this. And that's exactly what we saw. Here's the velocity projected on a line through the black hole and subtracting all the background. So this black hole is about 10 to the 9th solar masses, a little more. In more detail, for those of you who are interested in how this works, this is a map that, let me show you where the black hole is, because you're not going to understand anything unless you see where the black hole is. So here are the two black holes, the same situation, that one is the data, the other is the model. And blue means the material is coming toward you. Red means the material is going away from you. Red shift. The color of the light is shifted to the red. So we can measure the black hole this way. And so this northern black hole is somewhere between 9 times 10 to the 8th and 2 times 10 to the 9th times the mass of the sun. Pretty big and beefy black holes. So there's another set of issues. How much time do I have? Does anybody know? I forgot when I started. Okay. So one of the curious things that people have discovered about black holes in the cores of galaxies is that the properties of the black hole are highly correlated with the very, very large-scale properties of the galaxies, which is very odd because you have to be very close to that black hole in order to even know it's there, right? I mean, there's lots and lots of mass in the galaxy. It's 1,000 times more mass in the galaxy than there is in a black hole. So unless you get very close, you don't even feel the gravity from the black hole. So why should the property, how does the black hole know what's happening in the whole rest of the galaxy? And how does the galaxy know that the black hole is there and therefore it should have a certain set of properties? Here's what the graph looks like. So this is the black hole mass in the center, and this is the spread in velocities of the central parts of the galaxy, the stars in the central parts of the galaxy. And they're pretty nicely correlated. They're even better correlated now than they were from this graph in 2002. So we asked ourselves, okay, we can measure the black hole mass, we can measure the bulge, and these are galaxies that are in the midst of colliding. Maybe during the collision is when they figure out that they're supposed to obey this odd relationship. So we asked ourselves, during a collision, do the black holes grow at the same speed as the velocity dispersion and causing them to evolve along the same scaling relationship? Or does one of them grow faster and then provide the limit for the other? So if the black hole grows first in these colliding galaxies, we should see black hole masses that are up here above this curve. They're more massive because they're growing faster. If the galaxy velocity dispersion grows first, we should see our galaxy's black holes lying below this curve. And why is this interesting? Well, if the black hole grew first and got to be really big, it can spew out energetic particles and very high energy radiation from the accretion disk around it, and maybe limit the formation of the central bulge and cause the velocity dispersion to stop growing. Okay, or as you form the bulge and the stars in the bulge, the star formation could use up the gas, and so none of it would be left to fall down onto the black hole. So that would limit the growth of the black hole. It could go either way. And this is what we found. So our galaxies lie above this curve, which suggests, at least in this kind of galaxy, that the black hole mass grows first, and the properties of the large-scale galaxy develop later. Okay, and then, so we want to say something about whether these black holes are eventually going to merge together. And part of why it's interesting is just to understand how the eventual outcome of a merger settles down, and how the black hole in the middle, which is now made up of the two black holes, actually manages to balance itself out with what's happening in the rest of the galaxy. But you may have been following the news. There's now gravitational wave detectors. They're called LIGO and Virgo and one other one in Japan. And they can detect gravitational waves that are emitted as black holes merge. They can't yet detect them as these supermassive black holes merge, but the principle is more or less the same. So if you look at a computer simulation of two galaxies merging together, this is by Meyer in Switzerland, here are two galaxies coming closer and closer together. Each one has a black hole in the center. And if there's not much gas in the nucleus, these black holes just go around and around and around each other, and it's like the Earth going around the sun. There's nothing to actually make the Earth merge with the sun unless you disturb it somehow. And you can disturb it by throwing a lot of gas at it, having drag against the gas, having shock waves in the gas, and you can end up with these two black holes merging. And their simulations said if there are gaseous disks in the very center of this galaxy, that might solve the problem and allow them to merge. And so one of the things we did was we looked at a bunch of galaxies, and 17 out of 17 of them at that point had big gaseous disks, several hundred parsecs across, up to 500 parsecs in size. They had fast rotational velocities, and in most cases, they're really vigorously forming stars. And so we think that these giant black holes, whose mass we can now measure, have a pretty good chance of eventually merging because there's so much gas lying around in the middle of the galaxies. I'll skip this slide and talk about gravitational waves. So these LIGO detectors have detected merging black holes that are tens of times the mass of the sun. And I'll tell you a little bit about how we're going to detect the ones that are 10 to the 9th times the mass of the sun. But this is exciting, and so I wanted to show you how this works. This is the strength of the gravitational wave. So what does that mean? A gravitational wave goes by and it actually changes the distance between 2 points. And if you are measuring distances very precisely, it'll change the distance in this direction differently than it'll change the distance in that direction. 2 perpendicular directions. That's called measuring the strain. And so there are these 2 sites where there are these detectors. And you start seeing a signal, and the signal gets to be faster and faster. So this is time. And the frequency of the signal goes up. It starts at low frequency, gets very high frequency. And then after the black holes merge, there's this little ring down. You can actually learn about the mass of the remaining black hole, the merged black hole, from looking at the detail of the now one big black hole kind of quivering and trying to recover from the fact that there was this huge collision. So the people who do the LIGO observatory made this into sound. So low frequency in time corresponds to deep notes in sound, and high frequency in time, like here, corresponds to high pitch. And so I'm going to try and play you the sound. And the first thing you'll hear is the background noise. So one of the tricks they have to play is to pull these signals out of the background. But then at the very end, you'll hear whoop, 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 and that's the 2 black holes merging. So here we go. I hope you can hear it. One of them is multiplied by to make it a higher frequency that's easier to hear. I don't know how many of you could hear the whoop. So the day after they announced this, everybody in our astronomy department, instead of saying hello in the morning, we said whoop. So how do we do this same thing for black holes that are 10 to the 9th times the mass of the sun instead of a few tens times the mass of the sun? So this is the frequency of the gravitational wave. And so we were looking with these LIGO detectors at very high frequencies, which is low mass black holes, and to look at the long wavelength, low frequency gravitational waves that we emitted by these giant 10 to the 9th solar mass black holes going around each other faster and faster. You have to have something that's really big to detect them. They have very long wavelengths. And so there's this thing called the International Pulsar Timing Array Pulsars are neutron stars that are rotating and emit very, very regular bleeps in radio frequencies. So you can use them as timers. And if a gravitational wave goes by near us in the galaxy where all these pulsars are lying around us within the inner kiloparsec or so of our galaxy, it's going to change the distances between the rotating neutron stars, the pulsars, and as they move, it'll change the frequency a little bit of their beeps that they do. So they would ordinarily go beep, 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 and if a gravitational wave goes by, it'll go beep, 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 much more rapidly. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different radio telescopes around the world. I made this last year. I think there are probably more by now. They're constantly monitoring as many pulsars as they possibly can to try and see if there's a very long wavelength gravitational wave that actually disturbs the positions and velocities of the pulsars that are lying all around us in space. Okay, so a summary is we can find the location and mass of these big black holes regardless of whether they're emitting X-rays or gamma rays or anything else. We just look at their gravity effects. We think we can say that these scaling relations happen in merging events because the black hole mass grows faster, and then it limits the amount of development of the bulge of the galaxy. We think there are disks of gas lying around in the middle of these galaxies which will make the two giant black holes merge faster. And we actually might be able to detect them merging within the next decade, I would guess, using these pulsar timing arrays. So do I have time to do my secret extra a little bit, or are you guys going to get antsy? Yeah? Okay. All right. The secrets are partly revealed using adaptive optics to image the living human retina. So why do you even need adaptive optics to image the retina? So it turns out that your lens and your cornea are attached to the rest of your eyeball imperfectly. And of course, it's transparent, you can look out, but it's not optically perfect. So in bright light, your pupil is very small, that's where the light goes into your eye. And you can't even see the imperfections because the pupil is smaller than where they are. But at night, when your pupil gets very big, you're actually looking through these imperfect attachments. How many of you at night see flares coming from streetlights or halos around headlights and stuff like that? That's what's happening. You're looking through this less perfect part of your eye. And this is actually pretty serious. We said before that as you look through a bigger and bigger telescope or aperture or pupil, in this case, 7mm pupil, 1mm pupil, if something is a perfect source of light, point source, the point source should get smaller and smaller because the diffraction limit is wavelength divided by telescope diameter or pupil diameter, lambda over d, and d is getting bigger and bigger. But it's pretty sad. This is what it actually looks like. So as the pupil gets bigger and bigger, you're uncovering the optical aberrations, and things get worse after a while rather than better. And what you do with adaptive optics is you get back to more or less the perfect imaging. So why does that matter? If you're studying how the eye works and how the visual cortex works, you want to be able to isolate individual rods and cones in the eye and actually probe them one by one and ask, what do you see? What is your perception? And if you're a physician, you want to be able to image the retina very, very clearly so as to see the progression of disease and maybe even catch retinal detachments before they happen, much before they happen, or macular degeneration, things like that. So the early adaptive optics systems at the University of Rochester, they're pretty much exactly like the early adaptive optics systems were for 3 and 4 meter telescopes, and I show you this because you can see the parts. Here's the computer. Here's the subject, Jason Porter. He is biting a bite bar, and his head is leaning against this bar on top of that thing. You have to stay still. This is much better now, but back then you have to stay still. Here's the deformable mirror. This was literally one that was used in an astronomy setup as well. This is the camera that's taking a picture. This is what's measuring the aberrations. And it was pretty cool. So you can actually see individual cone photoreceptors. Those are the color vision detectors. Each one of these detects, operates your color vision. This is the shadow of a blood vessel, which is in front of your retina. It's backwards. Your blood vessels and your nerve fiber laser are in front of the retina, because the retina needs lots of blood supply, and it gets that from the back, so they can't mess up the blood supply. And you can actually make a 3D sectioning of the retina. The retina is kind of fixed, so here are the photodetectors, here's the nerve fiber laser layer, and so forth. So you can study color vision. We have 3 kinds of cones that are sensitive to blue light, green light, and red light. And it turns out that there's a huge variation in how those cones are laid out in the retinas of people who have perfectly normal color vision. So here's somebody who's got a pretty even distribution of green cones and a lot more red cones than green cones. Here's somebody who's got blobby distribution of green cones and sort of the same number of green cones and red cones. Both of them have perfectly normal color vision as measured by any of the tests that our doctors give us, including looking at the fuzzy things and saying, I see a number 9, or I see a letter J, or whatever. So your brain is doing incredible processing. You're born with fewer or more of these different sets of cones, and we somehow learn that yellow is yellow because somebody tells us, oh, that's yellow. And there's no way to know whether my yellow is the same as your yellow, because we probably have different retinal distribution of cones, but we can, our brains can get used to the fact that yellow is yellow. The other amazing thing, which I really don't understand, is both of these people can look at a white wall. White is all different colors, right? Why don't they see very non-uniform distribution of colors on the wall? And yet white walls look completely smooth to me. I hope they look smooth to you. So somehow your brain is also integrating over a large patch of this in order to see things like smooth surfaces. It's pretty amazing. And the final slide, you could use adaptive optics to actually, oops, it's not going to work. I'm sorry. Somehow the movies don't survive here. This is a capillary, and you can actually watch individual white blood cells zoom their way around the capillaries. And you can measure the speed and the number of them, and that's a measure of how healthy your retina is. When Austin Rorda up at Berkeley first figured out how to do this, he had a grad student actually counting blood cells, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now there's AI, so that's much better. Okay, thank you very much.